All right, thanks for joining WPI Services at the Winter Simulation Conference here at the JW Marriott in Washington, D.C. I'm Justin Wolf, and today we're going to be talking a little bit about our optimization tool suite, known as Opus Suite. Opus Suite's designed to allow an analyst to analyze the system, optimize its performance, and simulate various outcomes. Basically, the concept is we're going to simplify life cycle decisions and cost calculations with the tool suite. Here in our quick presentation before we get into the demo, we're going to look at the optimization trade space, some of our unique capabilities. We'll talk a little bit about some of the current customers using Opus Suite and some of the programs using Opus Suite to optimize and simulate performance. We'll look at how Opus Suite is used for decision support. And we'll wrap it up and get a little more detail and some backup slides that are available offline. Then we'll step into the demo. Let's talk about the optimization trade space. Opus Suite's primary function is to find the optimal balance between operational effectiveness and overall cost. Essentially, we need to take information about the technical system. That's the reliability, maintainability information. Information about the support solution, such as where we have contractors repairing items, maybe an organic depot in our operational sites. And then how we intend to operate the system. That could be as simple as flight hours per year, or as complex as understanding every single mission, over the course of a 20-year life cycle. This allows us to understand this blue dot that's in the center of the screen. This indicates where we are performing from an effectiveness standpoint and a cost perspective. From here, we have a trade space. We can either increase capability and maintain the current budget levels, or we can reduce cost and maintain our current levels of effectiveness, or some measure in between. And then over time, we need to understand, how things like reliability growth, how changes in effectiveness, how changes in capability come together to allow us to move the curve one way or the other. It's important to note, Opus Suite has undergone a full V&V and is the tool of record for this type of logistics analysis, readiness simulation, and lifecycle cost in the UK and Australia. Additionally, the defense components of 30 countries are using Opus Suite. When we look at some of the unique capabilities for this type of strategic and tactical analysis, to bring a decision support capability to this systems and logistics trade space, we're going to look at Opus 10 first. That's our mathematical optimization engine. We have Simlox, that's our Monte Carlo simulation tool, and Catlock, which is our lifecycle cost tool. Essentially, this is going to allow us to optimize our product support concept over time, dimension our facilities, personnel, and equipment, and perform detailed manpower trade studies. We'll also be able to do a detailed location of repair analysis, optimize our resources, including test equipment, support equipment, simulate different mission effectiveness calculations, look at like sortie generation rate, things like that, and do a complete readiness-based sparing. Within Opus Suite, there's no computational limits, and we have a pretty robust capability to import Mil Standard 1388 data or the new GIA 0007 LSAR data sources. After we've done this kind of optimization analysis, it's important to be able to visualize cost, and that's where Catlock comes in quite useful in understanding the lifecycle cost capabilities, costs related to any of our key performance parameters, doing budgeting, forecasting, and comparing these different solutions, full suite of sensitivity analyses and things like that. So let's look at some of our software users. About 600 licenses installed at about 150 unique customer sites in 30 countries on 5 continents. In addition to our defense software users, we also work with a number of oil and gas providers, wind power providers, a little bit of medical work, and some commercial aviation as well. When we look at some of the example programs that we've supported, we have experience on more than 100 programs, including some pretty complex performance-based logistics programs. And those include CH-47 on the rotary wing side, F-18, that's a jet. We have some commercial things like the S-92, multiple ship programs, land vehicle programs like the Leopard tank, and more. So why Opus Suite for decision support? One of the key things that we're going to look at here is our system operations, our readiness, and lifecycle cost analysis. The primary benefit of this kind of optimization and simulation is being able to understand not only the mission time that we're going to accomplish, but also its variability over time. Look at things like how particular spikes in utilization affect our ability to bring resources to bear, our ability to do preventive maintenance, possible damage modes that come from our usage. Look at our ASABO, mean downtime, different metrics like that. And the key here is optimizing manpower, material, resources, all in one single model. One of the really unique aspects of the tool is this level and location of repair analysis. What we found, we compare this to other methods, is we can lower manpower costs by more than 20%. And this is really key. In the defense space and in many industries, manpower runs about 50 to 60% of our total life cycle cost. While material is critical to availability, when it comes to LCC, spare parts is less than 5%. So when we look at the criticality and the importance of optimizing our people, it's important to simulate some different outcomes, identify our solution robustness, and perform the what-if analysis to see the impact of things like investment in reliability growth, the investment in new test equipment, and understand how these things may change over time. And finally, performing the spare parts analyses is critical. Again, to availability. Not necessarily to the life cycle cost, but certainly aircraft availability, ship availability, things like that. And again, speaking about optimization over time, it's also critical that we be able to understand how reliability growth and how ramp up and ramp down of our systems actually impacts the ASABO over time and impacts our spare parts and readiness-based sparing levels. All this comes together to create a really holistic LCC model for true optimization. We're going to consider all aspects to include our test and support equipment, as well as our personnel and training requirements. And this has been proven on more than 100 different programs in 30 countries. And again, primarily defense, but also oil and gas, some power, some medical systems, and commercial aviation. And we want to identify our performance against some of those key parameters, including our sortie generation rate, logistics footprint, cost per flight hour, and more. And what we're seeing here on the three charts is how resource utilization and our operational limitations kind of come together to create a life cycle cost. And we'll dig into this in a little more detail in the actual demo itself. So when we look at Opus Suite, again, we have three parts to the tool. Opus 10, that's mathematical optimization, SimLox, and CatLock. So we'll start with Opus 10. What Opus 10 allows us to do is build a detailed multi-indenture, multi-echelon model. In this case, we're going to look at a fictitious aircraft system. We can just click through some of this. We've got an engine, landing gear, flight control systems, environmental control systems, and this will be consistent throughout the model. Second, we have the support organization that we can see here where we have a workshop. This could be a contractor repair facility. We have an organic depot. We have an international site that has an eye-level capability. We have three CONUS support organizations, or two CONUS support organizations supporting 3 flight squadrons. In total, we have 45 systems, and they have a unit price you can see here. And then I can click through some of these tables, and we can just see some of the other interesting features. This is sort of our table view here of our individual items. And maybe of interest, I'll blow this up. Things like item repair information, our system deployment, how we intend to operate these systems, and utilization factors. Some preventive maintenance information, and some individual stock allocations. Maybe this is data provided by a contractor for their proposed spare parts list. Typically, the first thing we do is run an optimization, and we'll do that now. And I'll zoom in here on this result. And we can see that based on this information, we'll look at availability first. We can just scroll and pick a point along the curve that we're interested in. And we'll pick that first point that's above 95%. We have one that's exactly 95%. And we can now understand some other factors about this besides availability. But we might be interested in our annual downtime. That's just really the inverse of availability. We can look at our mean downtime. So instead of total, we can look at the average length of our downtime events. Maybe, fill rate, supply metrics, things like that. Now you notice this stepped curve. This is the difference between optimizing for fill rate versus optimizing for aircraft availability. Those two metrics don't necessarily agree. We can optimize to fill rate, but that's a suboptimal metric. We'll go back to availability. I'll zoom in again. We're going to do a lot of analysis now with this 95% point. I'll slide our little screen viewer out of the way. We can look at some quick results. And I can see that, again, I have an aircraft availability of 95% with a mean downtime, number of back orders, and waiting time for spares. I can look at my spare parts list that meets those particular requirements. This will be the particular LRUs and the particular location and the stock size required to meet that 95% A sub O. Now, this is entirely asymmetric. Each site, each location will have its own unique spare parts list. We can look at resource results. We can look at some system results, system by system, specific numbers. If I go back to the graph, we can also view this here by unchecking this total over stations. And we can see the individual results for each individual site. One of the challenges I think an analyst often has is understanding how this overarching result is created, maybe identifying cost drivers, looking at different things like that. So if I click on Analyze, and then I'll expand this out. And we can start, we have a little chart here that shows our actions per year. We could also look at just overarching failure rates, just look at repair actions for those consumable items. We can look at items consumed, or we can just focus on preventative maintenance. But we'll look at total actions per year. And this is going to allow us to identify, I'll scroll over a little bit, some of our cost drivers in the system. And we can see that as we would expect, the primary weapon system itself is the overarching cost driver. Followed closely, as we would also expect, by the engine. It's typically the most expensive part of the aircraft. There's a lot of preventive maintenance and corrective maintenance. And then you'll notice also that some of the LRUs within the engine are the next 6 cost drivers. This would certainly tell an analyst that they might want to work with the reliability team to make sure they have confident data, and that they're very certain of the data in this sector. Getting real, solid, confident data for some of the consumable items, perhaps, some of these items in the lower left, maybe not as important. We're not necessarily as concerned with having really precise, really accurate data for these items, because they just don't drive the model. And we can see kind of where they perform in our cost driver index. You can see that's a much lower number than some of the factors up here at the top. So once we're confident that we have, a model that's fairly robust, fairly defensible, and we've created this sort of optimal solution, the next step is understanding how this optimal solution will actually perform in a real-world scenario. This is where Simlox is really critical, the simulation capability, and really what brings us here today. So Simlox allows us to quickly import our results from Opus 10, that output file, with that stock allocation, with that resource, with that set of repair solutions when we performed our LoRa, and understand how our flight profile that we use to generate that sort of overarching utilization factor will actually perform. And so we can see here that we have 6 different missions that we intend to fly. We have this surveillance mission. We have some random utilization, 2 different random utilizations actually. and then some regular squadron training missions. We're going to apply those into our systems through this operational profile table and our mission type table. So we'll apply these to the systems and go fly a given operational profile. We can look at that here and we can see how this looks. I'll expand this a bit. And so now we have a really detailed perspective on utilization. We can see that we have a spike, over the course of a year. There's 8,760 hours in a year. We're going to fly 2,600 missions for a total number of mission hours of 8,044, and that's across all of our systems. If I zoom in here, we can just look at a sliver in time of this operational profile, and you can see how there's these daily spikes where at some period of time we may have 8 systems in use. And so this is very interesting because this no longer requires this sort of average utilization that's very steady state over time. We can see how our dimension system will actually perform in the real world. So go back to the model view. We'll run this simulation. And again, we're going to simulate 25 replications over a year of operations. And we'll be able to see that, we'll go to our mission results. In this particular case, that 95% aircraft availability resulted in a 99.64% mission success rate. And you can see that we actually started all of our missions. So we actually had a sortie generation rate of 100%. We had a mission completion rate of 99.64. This is very interesting. We can look at this over some of our system results, and we can see that that actual mission profile was only a 3.5% utilization. I'll cancel that zoom. See, we have a lot of availability. Some amount of our unavailability is waiting for items. Some amount is waiting for resources. In this case, that's people and test equipment. And then we have some systems in active repair and active preventative maintenance. We're looking at the totals there. We can look at how this varies over time, and we can see these drastic spikes. As we go out for these surges in our utilization, these little spikes in yellow down at the bottom, we have more failures as we have more systems in operation. We recover from those during these troughs, and then we're kind of hit by them again that next time we go use the system. So, the senior leadership oftentimes equates A sub O for mission success. And that's not really the right answer. But they might say, well, hey, look, we really only meant for you to complete 95% of your missions. So let's take a look at how we can reduce your budget and figure out, we'll play some what-if games now and try to figure out, your capability to meet future needs with some different budget profiles. And in the case of sequestration, that might be cutting your budget by 20%. Your manpower budget by 20%, rather. And so we can look at that, and we can see the impact of a 20% cut in utilization of those manpower and personnel accounts. So again, we can perform another simulation just by, after cutting that manpower slightly. And we can see that it didn't actually have a big impact on our utilization. And in fact, by better spending, we can say, we can actually increase our total mission success rate. And that's through bringing in a different mix. So if we say, hey, look, we're going to cut our manpower by 20%, but we're going to actually optimize. We're going to put the right spares in the right place at the right time and take a look at how we actually use these systems, make sure that we have material available to support those spikes and those surges, in particular, again, going back to our stock allocation and our mission type and our operational profile. You can see that we have, these sort of very scheduled spikes in utilization. And if I go back to our profile view, you can see that we have these spikes here that aren't random. They're very predictable. It's not the random air interdiction missions that are driving these. It's these long surveillance missions that are driving these spikes. So we can say, well, if we optimize over time, what's the impact? can we cut 20% of our manpower if we actually take some of this time-phased optimization into account? And so we can do that. And we did. And we can show that even with the 20% cut in our budget, by doing a little better job of planning for a non-steady state scenario, we can actually impact this quite substantially. And if we go to our system results and look at that second case, you can see that, even with that cut, by putting the right people in the right place, not assuming a steady state scenario, we can actually do a much better job of meeting some of our mission goals. And again, because our mission results were pretty high to begin with, we kind of had some robustness in the solution. So there was plenty of room to move things around, do things the right way. Kind of very interesting, way to think about this, that material accounts substantially. And again, if we go back to our base case, we can look at the system results, and we can see that, manpower seems to be contributing to unavailability, but in both cases, materials really has a sort of substantial impact. So if somebody says, well, we're not going to perform preventative maintenance on the system and we're going to delay some of our corrective maintenance, has the same impact from a dollars perspective. Again, keeping in mind that people are actually really expensive. So if we pull in that case and we simulate those results, or that particular case to generate results, we can see that we have this huge amount of unavailability now due to material by delaying preventative maintenance and not getting the right parts in the right place at the right time. You can see we don't have a lot of waiting for people, so that means we have idle resources. We can look at some of those resource results. So we end up having this case where we have now people available that aren't really doing anything. So we're paying for, and we have this pretty major hit to our mission capability. We're dropping from, the high 99% down to about an 86% mission completion rate. Maybe this is still acceptable, but it certainly, for the same budget, has a much larger impact than the 20% cut in manpower. So, all this kind of just gives us the ability to do some of this cost comparison and capability comparison through simulation. The kind of final piece of this is this perspective on CATLOG. And CATLOG allows us to then dig into these results in a little more detail. So what we're looking at here is our cost breakdown structure. These are all the different accounts that we want to consider. And we have some material here, and if I had a bigger screen, we could dig into some of this a little bit more. But we have this failure rates that we might look at. We might look at some of the different cost items, maybe our resource investments. We're looking at fuel there by year, by location. We can look at really any different parameter. Some of these don't necessarily have any values. The key here, those are results. We can compare a couple of different solutions, a couple of different outcomes. And again, keeping in mind that we're just looking at that same high-level view of life cycle cost. But then we can start digging into this with a little more detail. And so I can expand all levels. Maybe not that many. Maybe we'll bring some of these back and not view every single item. It'll get a little busy on the screen. I'll click OK. And we can see that, the majority of our, life cycle cost, at least for this particular scenario, is in acquisition. And then we have some other different accounts. And I'll hide a bunch of these and bring some of these back. Make it a little more visible. We can see that we have some recurring costs. We have some additional investments in spares, and we have some yearly operations costs, and then just a small sliver of termination costs. We might want to consider maybe what are some of the material drivers in the system. Maybe we can compare these side by side, and I'll, again, shrink some of this up. We'll just show the top 5 material drivers, not including the aircraft itself. So maybe we'll look inside the communication system and identify the top 5 drivers. and we can see how that looks. And we can see that, within the two different potential solutions, we have some different costs where the one's clearly more expensive than the other from a comms perspective. Maybe if somebody's interested in the, let's say the landing gear, actually we knew the engine's the real driver, right? So we can look at that. We can look at the top 5 drivers from an engine perspective. Maybe we don't want to look at the actual LRU of the engine, but maybe some of the SRUs and LRUs within that system. And we can kind of do some cost comparison of some of these different solutions. Going back to the overarching results, we might want to look at this over time. And so we can drag time over and we can see how we're going to spend money in different years based on our operations profile, based on the failure rates and failure modes of the system. Again, we're looking at 20 years there, so maybe not a little too much to see on the screen. We can always come here instead of showing all. We can just show the top 5 years. But we can do some, cost control, cost comparison. As you'd expect, in the first 5 years, the majority of your cost is system phase-in, as we buy systems, buy spares, buy material. We can drag time back. Maybe we want to look at some of our resources or really anything. So we can dig into this in as much detail, as little detail as we want to understand how, again, going back to the optimal solution, how this optimal solution that we see here, the traditional availability and cost curve, will actually perform over time. Again, from a simulation perspective, looking at the simulation across a couple of different cases. And then doing cost control and understanding how these different costs are going to come together to create an optimal solution that's affordable to the customer and meets their specific mission objectives. This is really important. I'll go to this chart next. Really important to perform this kind of analysis across the life cycle. This could be early on in a conceptual phase, later on in an acquisition of a program, through development and production, and then ultimately, with that feedback from operations, to continually improve the system capability and continually improve our ability to estimate, future capabilities. I think one of the other things we really focus on quite a bit is this requirement specification phase. One thing that Opus is really quite useful for, instead of a deterministic sort of an input, give me the solution for a 95% availability point, we can show a customer how perhaps their requirement here, might be too high. Maybe they can accept slightly lower availability to save a substantial amount of money. That might be something that they're interested in seeing. So we've done that quite a bit, where some of these requirements are always tradable given the right sort of motivation. And we're at a time now where perhaps this delta in cost far outweighs this incremental decrease in capability. So we can show people, here that capability, and then we can also show them how this difference in capability will, translate to some mission success, some mission effectiveness, sortie generation rate, or cost per flight hour kind of a metric. And so, I guess, in summary, a brief summary, when we look at some of the benefits of doing this kind of analysis, we've shown that we can lower our total ownership costs by more than 15% through the optimization of manpower, material, and resources. We optimize our life cycle costs as a function of readiness objectives. This is going to allow us to create defensible and realistic budgets tied to results. So instead of this approach of, what is the answer, what is our budget, and then we'll figure out how to spend the money, why don't we try to tie something to an actual capability? Opus Suite's been integrated with multiple legacy data sources to optimize its capability based on real-world data, and I think that's really key. We want to have an effective result that's also, realistic, also contains, real-world reliability data, real results. And then lastly, we want to demonstrate our ability to lower manpower costs, again, given that it's the largest account, and our repair strategy location by location. And Opus provides the capability to optimize over time, whether that's ramp up and ramp down, changes in reliability, or maybe it's tech refresh, to lower total ownership costs and optimize our lifecycle costs based on these mission objectives. We're going to optimize all aspects of our logistics system, including maintenance and resources, material, and quantities of systems required to perform a desired mission affordably. We're going to perform some detailed trade studies and business case analyses for should costs and program contract evaluations. And keep in mind, Opus Suite is a COTS product with a broad base of users. It's been under continuous development for over 40 years, and this is going to ensure, this broad base of users ensures that the product remains usable, affordable, supported, and extendable to future requirements. Our user base, really has a big part to say in our continuous development. And finally, I'm assuming I'll get a question here about the data requirements and how difficult it is to build these sort of very robust, very capable models. And really, preliminary model development using, I'll say, the bare bones data elements are going to provide the 80% solution. We have about 300 potential input variables that we can use. But really, the only required data is, some item identifier, item failure rates, the acquisition costs, the notional configuration of our system, the duty cycle or utilization factors, the system repair metrics and item repair metrics, and our transportation profiles. Once we have that, we can really start to build a robust 80% solution that we can use to continually develop and continuously optimize our capability. I'd like to thank everybody for coming in and sitting through this brief demo on Opus Suite. And if you have any questions, please use this time to ask those. I'm going to turn off the online demo at this point and wish everyone a good evening. Thanks.